Okay, when we verify trig identities, first of all, a trig identity, when you think of an identity, you need to be thinking that there's an equation. Okay, so there's a difference between an expression and an equation. In an equation, we have an equal sign. When we verify trig identities, it's really, really important to work with one side of the equation. So we're proving that the two sides are equal. We're not assuming that the two sides are equal. We're going to prove that the two sides are equal. So if we don't know that they're equal, we can't work with both sides. We can't manipulate both sides of the equation to prove that one side is the same exact thing as the other side. So keep that in mind when we're trying to prove an identity. You can't assume that it's true. Therefore, you pick one side of the equation and you transform it to prove that it is indeed equal to the right side. So what I usually do is I work with the more complicated side of the equation. So the side of the equation that gives us more stuff. That's what I mean by more complicated. So work with the more complicated side of the equation. And I'll just put EQN for equation. Step 2, we're going to look to factor. So we're going to use all of our algebraic techniques that we know how to do back to algebra 1. Look to, I don't even know where the word "the" came from. Look to factor, add fractions, and that's before algebra 1. But we're going to add fractions with variables. So that's algebra 2-ish. And then square a binomial. Square means raise it to the second power. Square a binomial. So a binomial is an expression with two terms. Create, this is a good one. Create a monomial denominator. So I'm going to give you examples of these. I actually already gave you an example denominator. I already gave you an example of creating a monomial denominator in the previous lesson, but I'll do it again here. And then use the fundamental identities. Use the fundamental identities. And those fundamental identities, remember, you need to know them like the back of your hand. Use those flashcards, please. And then, do you love the color coding here? And then we're going to convert to sines and cosines. Now, we don't always have to do this, and we don't always have to go with, step 2, step 3, step 4 in order. Sometimes we just go to step 4. It's not always the most efficient way. So that's why I'm going to say convert to sines and cosines if numbers 1 through 3 don't help. If numbers 1 through 3 don't help, or doesn't help. And then last but not least, I'm gonna have to find that color there. There we go. I think it's actually this color. Don't stare at the problem. Don't just stare at the problem. If you stare at the problem and say, I don't know where to begin, I don't know what to do, you're never going to get there. It's still going to be looking back at you. So do something. Try taking a road, and if it feels like you're going off road and you're going nowhere, or you're going somewhere that's really off course, you can always start at the beginning again. It's not like you have to find your way back. You just stop and go back to the beginning and try again. Paths that lead to dead ends give you insights. So dead end paths give you insights to that particular problem and others. Dead end paths give you insights. Okay, so here's our first verify. Now remember, we're going to work with the more complicated side of the equation. So I believe that the more complicated side, the one that gives us more to work with, is the left-hand side. We're going to take that left-hand side of the equation and we're going to try to transform it so that it looks like the right-hand side. So my very first step here is to work with the fractions. Now I don't necessarily need to add fractions, but I do need to be able to work with the fractions. So there's a couple different ways that we can do this problem, and one way that I'm going to do this problem is by separating out that denominator. So secant squared of theta over secant squared minus 1 over secant squared. And then I'm just going to put the equal sign there. Now when the left-hand side looks exactly like the right-hand side, that's when we know we're done. Step 2, anything over itself is 1. Minus 1 over secant squared, well that's cosine squared of theta, and 1 minus cosine squared is sine squared. So sine squared equals sine squared, and that's how we know we are done. Check. There's another way to do this problem, and it all depends on what you see. So when you're using those flashcards, sometimes you see one route that will take you to the answer. So secant squared minus 1 is the same thing as tangent squared of theta. So I tan by the c, 1 plus tangent squared equals secant squared. Well, if I subtract 1 from both sides, I get tangent squared. So tangent squared over secant squared. And then I'm going to separate these two out. Tangent squared times 1 over secant squared. And then we're going to say tangent squared is sine squared over cosine squared. And 1 over secant squared is cosine squared. And these cosine squareds cancel out. Now notice how I'm not just leaving it right there. My fourth step is to say sine squared of theta, and then that's equal to sine squared of theta. Right? There we go. So either one of those ways is right. It all depends on, you know, where your brain's going with it and what you see. And what you see might be different from what I see or what your neighbor sees, because I'm sure they're sitting home right now doing pre-calculus and trigonometry and all that stuff. But I mean your neighbor in class, you know, or your peer, your friend, classmate. Everybody kind of sees it a different way. So there are different ways of getting the right answer on these, but they all have to be sound. They all have to have sound fundamental identities that we're using and sound fundamental algebraic skills that are accurate.